Hello. This is, I guess we'll call it part two of my um, recorded lecture to make up for um, not having a lecture on July 25th. In part one, we sort of walked through Prim's algorithm. In this lecture, I want to talk about Kruskal's algorithm and um, walk through implementing that. Um, so if you remember from class, before we do Kruskal's, we need to be able to talk about union finds. I'm not going to motivate them again. I encourage you to watch the lecture for that. But let's talk about how to implement union finds real quick. Okay. So great. The idea of a union find is a data structure that supports insertion, or this is a data structure that basically tracks a collection of disjoint sets. Right. So the idea is I have some space of things, right? Whatever. And a union find lets me keep track of, or it lets me sort of partition these into classes like this. Right. So maybe these two go together and maybe this one is in its own class. Right. Um, and it lets me do this efficiently for some sort of nice definition of efficiently. And in particular, it supports the following operations. So we can insert. This is like adding a point to our set. And when we add a point, we sort of assume that it exists in its own set. There's find, which is where given a point, we identify what set it belongs to, right? So given this point, we maybe return this set. This point, we return the same set. This point, we return this set. This point, we return this set, and so on. And then we have a union operation, which takes two points, or maybe two sets, and or it takes 2 points and it merges their associated sets together. So maybe I take those 2 points and I merge them into one big set like this, right? And the idea here is every point is in its own class, uh, and sort of we can union things together, which makes it so that if two things were in the same class and another two things were in the same class, and we join them, then all four are now in the same class, right? Um, so that's the idea. And just as a refresher, the way we use this for Kruskals is in Kruskals, we have a graph, right? And when we we start with the set of vertices of this graph and we insert edges one by one based on the weight of that edge or in increasing order of the weight. And we want to make sure that we never create a cycle. And the way to do that is by making sure that the endpoints, so if we're adding a new edge, the two endpoints of that edge are not already connected to each other, right? So we can keep track of maybe have all of our vertices be like the objects in this space over here. And then these sets represent vertices that are somehow connected to each other. So like maybe there's like a sequence of edges like this or something. I don't know, right? These vertices would all be connected via some sequence of edges, right? But there would be no connection between any vertex here and any vertex here. So what do I do? I start by inserting every vertex. Right. When I add an edge, or adding an edge, maybe I'll call it u comma v, or maybe I should u arrow v. We find the set associated to u, we find the set associated to v, and we assert that find u does not equal find V, right? If find U and find V return the same set, then we know that U and V are somehow already connected, which means that adding this edge would create a cycle. So when I say assert relay, I mean if these are equal, then we just skip it, right? And then after adding U comma V, we just union U comma V. So the set of all things reachable from U and the set of all things reachable from V are now merged because U and V are now mutually reachable, right? And I'm sort of playing fast and loose, just kind of calling these undirected edges. But you sort of you care about this either way, right? Okay. So this is all stuff that we sort of talked about in lecture. Now I want to talk about how we can actually implement a union find. For the interest of time, I'm not gonna like I'm not gonna do a ton of work sort of trying to motivate this or trying to like build it from the ground up. I'm also not going to talk about the complexity analysis of this because it's a little bit tricky. But let's just get started. The idea of the union find is we store a set of classes, right? Right. A class is a set that's disjoint from all the other sets. Um, and we'll say each class is a tree. Okay. So insert is just create a singleton tree. Find is given a node, or maybe I should say each class is a tree. The vertices are the elements of the class. Right. So we can say given a node, traverse up to the root. And return that. Right. This way, if two vertices are in the same tree, in other words, two elements are in the same class, they'll necessarily have the same root because each tree has a unique root. Right. And then union, I'm just going to kind of draw this out. So if we have a tree like this, and we have a tree like this, union just inserts an edge from here to here, so that these are now all one tree, right? So that if now we try to like walk up this node, we go up, 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 and we end up at this root, so that this is no longer a root, right? That's union. Now there's a couple of so maybe the thing to say is like this by itself isn't necessarily isn't necessarily very good, right? Because you might notice like we could start with a bunch of singleton trees like this, right? And then we do a bunch of union operations where we union like I with I plus one, right? And this ends up creating a pointer like this and a pointer like this and a pointer like this. And so now to find the tree associated with this or to find the set associated with this node, we have to walk up the entire set. And this is theta of n, right? Which is bad. Right? If I was going to do something theta of n, I would just run depth first search and I'd like detect my cycles that way, right? So there's the point of union find is we want something that looks like roughly constant time here and here, right? So clearly this by itself isn't it, right? So there's two sort of optimizations that we can apply on top of this. And again, I'm not going to like try to motivate these in any further detail than they help improve the time complexity. But one of them is so when we union, we always point the smaller. We always point the smaller tree towards the larger tree. right? So if I have, so in this situation, for example, right, where I have like uh 1, 2, 3, 4 maybe, and I union this with this one, right? Now if I go to union this with this, that's fine. Um, and this with this. Okay, I guess that doesn't really help yet. But anyway, by smaller, I mean the total number of what do I actually want to say here? Yes. Okay, sorry. We point the smaller tree towards the larger tree, but in particular, we point it towards the root of the larger tree, right? So this is something we can do, right? We've got these four nodes, right? I do this. When I'm trying to union this with this, I or maybe I'm trying to union this thing with this element, so I find the root that gives me this one, and then the smaller one is the one on the right, and so I can draw an edge like that, or I can call its parent the root there, right? And then same thing here, I can call its parent the root here, and so now I get something that looks constant time, right? If I want to find a representative of this one, I just have to traverse one edge, and the same goes no matter what, right? And then if you want, you can think about having a sort of self loop here, so that everything has one outgoing edge. Okay. The other thing we do, so in particular, here, the size refers to um, the total number of descendants, right? So not necessarily not the size of the class, not the size of the equivalence class, but the size like in the representation of how many total things eventually point up to this node, right? So we might have something like this, right? Maybe this one points here. And so the size of this node is going to be 1, 2, 3, 4, right? And if we're then unioning it against something like against this one, maybe, right? The size of this is 2. So we get the uh bigger one. Yeah, okay. So if we're merging this one and this one, right? We find their roots first, and then we say the smaller one points to the bigger one, right? So this is the smaller one, this is the bigger one. So we point this way, right? The total size of this node is 1, 2, 3, 4. The total size of this is 1, 2, 3, 4, 5, 6, 7. And so the idea here is now we can prevent this this sort of degenerate linked list thing from happening. Um, okay, so we do that. This in particular means that we need to store the size, which will be important. The other thing that we do is when we're finding, we kind of, what's the word? We forward all the arrows along, right? So if I'm trying to find a representative of this node, right? I go up here, I see, okay, this is the parent. This still has a parent, so I'm going to go up here. While I do that, I'm also going to erase and redraw this edge to go up here, right? And then if I traverse up one more time, I'm going to erase and redraw like basically both of these edges to go up here, right? And now I found the root, right? So after I find on one node, I'm guaranteed sort of that like all of the nodes along that path are now pointing directly to the root, right? So I do this to try to keep the depth keep depth as low as possible, right? So what I'll say here is maybe like forward edges up as we go. Okay, and it turns out that if you and again, I want to say the root of. If it turns out if you implement union and find correctly, where you sort of find the root and then point it towards the larger tree, and you find the root and you point it towards or the it turns out if you implement these two optimizations, the overall complexity of this looks constant. Um, as I mentioned in class, it actually looks something like inverse Ackermann. Um, I encourage you to Google this. I'm not going to talk about it. Okay, so that's it for union finds. Um, let's implement things. Pull it up real quick. Okay, here we go. All right. So this is all of the sort of prims code that we had from last time. You'll notice I added a little bit to like I added this grab destroy function, which just goes through, frees up all of the lists, and makes it so that I'm not leaking memory anymore. And then this priority queue destroy, and then in prims we free the frontier, and then in main I've allocated two separate graphs. Right, there's the original graph and there's a spanning tree. I just free both of those. Right, and so now if I sort of just there we go. Right, if I run it, it gives me the same output. And then if I if I leak check, zero leaks. Great. Okay, so I want to start by implementing a union find, right? So maybe I'll say union find dot h if and def. Okay. Now, there's a couple ways to do this. The sort of extensible way is to have every sort of vertex be its own node, and it has like pointers and stuff. Um, that's great if we're sort of adding an arbitrary number of things, but here I think all we really need to do, like we know exactly how many things we're gonna have. So um, we know that the maximum number of things here is just gonna be the maximum number of elements total is just gonna be the number of vertices. So I can just say int uh, num elements. And then I want an array of pointers to the parent, right? So the way I'm building this tree is every vertex has a unique parent instead of a parent having a bunch of children. So I'm gonna have an array of pointers to the parent. So I'll say parents, and then I need the sizes, right? And so now I'll say maybe struct union find uf init in num elements. Okay, so this will initialize it. Here's our constructor. Now I don't need to worry about insert because I'm sort of assuming that we've already started by allocating, or we've started by inserting everything that we care about. What else do I need? I need union. So I'll say void uf union. This will take uh, the union find structure that we're doing a union on. This will take int a and int b, and these are the two elements that we're unioning. And then here I want to say int uf find. So this will take the ID of the element that we want to find, the root of, and this will return the index of the root. Right. So we're just operating based on indices. In a sort of more complete implementation, maybe you would want to say like struct uf node or something like this, and this would have a struct uf node parent and an int size, and then your union find would have like nodes or something like this. Like maybe it would be an array of nodes. And then you would just like insert into this or whatever. But we don't need to do that. So we don't have to deal with like dynamically managing things. And if you were doing that, then instead of ints here, these would be like this would be UF node, UF node, UF node, and UF node. But this is, I think, just easier. So, all right, let's implement our things. So we'll start by including my header and then copy over the functions that I need to implement. Right, okay. So obviously I'm going to need standard lib. Let's start by allocating space. Okay. And this is what we're eventually going to return. Right. Now, the things that I need to initialize are num elements, parents, and sizes. So num elements is very easy, right? I can just set it to num elements. Parents and sizes is a little bit more interesting. So for starters, let me start by allocating the appropriate arrays. So we can say parents equals pass to an int, calloc. The count is going to be the num elements. The size is size of int, right? And then it's the same thing for sizes, right? But now we actually have to initialize these, right? So for sizes, since every class is starting with just one node, all of the sizes can start at 0. So we'll say for int I equals 0, I is less than num elements, I plus plus, and here we'll do our initializations. We can say UF sizes at I equals, sorry, the sizes all start at 1. I don't know if I said 0 or 1 before, but they should all start at 1 because they're all sort of singleton trees. The thing for parents, every vertex is starting off as the root of its own tree. So we're going to sort of denote that by having its parent be itself, right? So we'll say UF parents I equals I, right? So this denotes root. Okay, so we've allocated our space. We've initialized everything. Before someone yells at me on Piazza, I'm just going to say void UF destroy. We're going to implement a free as well. Okay, so obviously I want to eventually free this thing. I want to say free UF parents, free UF sizes, and then free the actual pointer. Great, okay, good enough. Okay, so we've got our initialize and our destroy. Now, maybe, okay, let's look at union, right? So the first thing I want to do is figure out who has a bigger size. So actually I need to call find here first, right? So int a, I'll call it like a representative equals UF find UF a, right? And then b representative equals UF find UF b, right? So we find the roots of both of these trees, and then we're going to merge, we're going to have the parent of the smaller root point to the larger root, right? So if UF sizes at A rep is greater than UF sizes at B rep, then we need B to point up to A. We're going to say UF parents, the parent of B is now A. Otherwise, we're going to say the parent of A is now B. And of course, when we do this, we also have to update the sizes, right? So if B now points up to A, then the size of A should increase by whatever the size of B was. Yeah, the size of A should increase by whatever the size of B was. So we're going to say UF size is A plus equals UF size is B, right? And then the same thing, but sort of backwards for this, right? Maybe take a moment to think about this, but anyway. So here's our union, easy enough. Now our find function, we're gonna say if so we're gonna do this recursively, right? If the thing that we're looking for is already a root, then we can just return the root. So if UF parents x equals x, return x, right? Nothing to do there. Otherwise, we know it's not, so we're going to say int root equals uf find. We're going to sort of recurse up one level. And then if you remember, we want to forward all of these edges. So once we found the root, we're going to tell x to directly point to the root. We're going to say uf parents x equals root, and then we can just return root, right? I think this is correct. I think this is a complete and correct implementation. So let's try it, I guess. What do I want to? Okay, this is our fake main function. Our real main function is here. And then I'll include union find. Oh, I should make sure to add this to my make file. And I'm actually going to call this now Kruskal. Okay, so let's start with just maybe 4 elements, right? And then I want to start by saying printf oh, okay. Maybe a helper function to add here is bool uf equivalent, right? This is going to return true if they're in the same class and false otherwise. And this should just be very easy because all we really need to do is compare their roots. Okay, you can have standard bool as a treat. Here we go. Now we can just return uf find a equals. Okay. Okay, so let's start by initializing it with 4. Printf we'll say uf equivalent 0 and 1. This should be false. Let's do like 0 and 3, right? Actually, let's do 0 and 1, also 0 and 3. Now we can uf union 0 and 1 together, and then maybe union 2 and 3 together, right? So now we should have 2 equivalence classes, one with 0 and 1, and one with 2 and 3. So now we can ask the same things, right? So 0 and 1 should now be true, 0 and 3 should still be false. Now if I union 1 with 2, everything should be equivalent, right? So if I do this again, this should print true, true, right? So we expect this to be false, false, true, false, and then true, true. This is by no means like a complete set of test cases. This is just for me to make sure that nothing blows up in my face. And then let's just free it when we're done. Okay. Non-void function does not return a value. Oh, okay, fine. Why don't you return 0? What? Oh, bro, okay. Why don't you return 0? Because it doesn't care when it's main. Okay, so 0, 0, 1, 0, 1, 1. 0, 0, 1, 0, 1, 1. Perfect. Okay, so clearly this is correct. That I mean, it's maybe not, but it looks correct, and that's what matters. Okay, so there's our union find. Let's implement Kruskals. Right, so it's gonna um, maybe I can start in the same way. So I can say like Kruskals.h. Um, okay. Um, and now I guess the only public function that I need, well, I need to include graph, obviously. The only function that I need is a what do I call it in prims? Did I just say prims MST? So we'll say like Kruskals MST. And this is just going to take a graph as input, right? And this is the only thing that we have to implement. So let's go ahead and implement that. Okay. I'll start with this function header. We know we're going to need union find. Let's start by creating our spanning tree. So right, as before, it's necessarily going to have the same, it's going to be on the same like set of vertices. So we can just build that and then return it here and then actually do the, like actually implement the algorithm here, right? So maybe Kruskal's algorithm. What do I want to say? I start by sorting the set of edges. So then I can loop through in increasing order of weight if an edge connects to connected vertices skip. Otherwise, add it. All right. This is not pseudocode, but maybe you get the point. Okay, so obviously I need my union find, and this is going to represent the connected components. So maybe I'll call it struct union find components equals UF init. And this is also going to be on the same number of vertices. And right now, everything starts in its own unique component. So the first thing I need to do is sort all the edges, right? That's this. I want to use qsort. Where's qsort? This is in standard lib. Okay, great. So maybe I should include standard lib. Okay. How do I want to sort the edges? I think I want the, oh gosh, this is going to be a problem, isn't it? Yeah, I need to pull out the list of all edges. And then sort that list. Which is fine. Pulling out the list of edges is going to be something like O of E, and sorting is going to be E log E anyway, so it's not really going to affect my time complexity. Not that that should matter, but fine. Let's do it. So, okay, let's do this. I have a thing for edge. Yep. So get edges. I'm just going to separate this into a separate. I'm going to put this into a separate function, so that I don't kind of mess with this. Okay. So I want this to return a pointer to an array of all of the edges in the graph, given a pointer to a graph, and it's going to, this is like an out parameter, it's going to write out the total number of edges that it found, right? So we can start by saying num edges equals 0. We need to know how much space to allocate. We'll say 4 int I equals 0, or I'm going to call this v because this is the vertex. V is less than g arrow num vertices, v plus plus. So we look at the number of edges outgoing from this vertex. So we say G lists for this vertex dot num edges. So we can say, num edges plus equals that. And now, if you remember, we have twice as many edges as we actually want because we've got one outgoing and one incoming. But we really want these to sort of count as the same edge. So we're going to divide num edges by 2. Right? This is only because it's undirected. Oh, stop it. Okay. Now that I know how many edges I need, I can allocate an array. The alloc, the count is going to be num edges. The size is going to be size of struct edge. And then I want to go through these in order, right? So I'm gonna sort of go through again for int v equals 0, v is less than g arrow num vertices v plus plus. Okay. Oh my God. Okay. My decision to not include the source as part of struct edge, I realized, okay, so I was rewatching the lecture video for prims that I uploaded yesterday or whatever. And it was sort of like that moment in a horror movie where you watch the main character do something that you like obviously know is stupid, but the main character doesn't know it. It was that, except it was me choosing to not include source inside here because like if I had, I wouldn't need any of the other like extra nonsense that we had to do for prims. Like I wouldn't have had to keep track of the predecessors and the distances and stuff because I would just have the edge and I would know the source, right? And so like if I sort by weight, it's automatically like keeping track of the appropriate source for that weight. So I now have 2 options available to me. Number one, I can keep like jumping through hoops to try to make up for that mistake, or I can go back and fix it. Um, I think I'm gonna go back and fix it. I think it's worth going back to fix. So let's go here and let's add int source, whatever. When I add an edge, I need to now keep track of the source. So if I jump to, oh, what am I even doing? Oh, I need to go to the C file. Graph.c, here we go. So for add edge, I need to keep the source. And then destination source weight. Perfect. Okay. Now I think we can still do all of the stuff that we were doing in prims because it's still correct. It's just more work than necessary, and maybe at some point it would be worth like going back and cleaning it up a little bit. But now at least the edge keeps track of both of its endpoints. Because who wouldn't? Like that's obvious, right? Okay, so we do this. We for each vertex so E is going to be the index of the edge. G lists v dot num edges, E plus plus. I'm going to start, into I equals 0. This is going to be like the index we write to. Okay. So I'm going to say edges at I plus plus equals G lists v dot edges E. Now, technically, this is incorrect because I only want to add each edge once. So as we did in sort of Prim's algorithm, I'm only going to add the edge if the source is smaller than the vertex. That way, each thing only gets added once, right? This is an arbitrary choice to make, but it works. Okay, so I'm going to say, struct edge. How about we call this I? No. Okay, struct edge equals G lists v dot edges E. If edge dot source is less than edge dot dest, then we do edges I++ equals edge. Great. And then here we can just return edges, right? And of course, we've already written to this pointer with the appropriate number of edges. Okay, so to sort all of the edges, I can say, int num edges equals 0, struct edge star edges equals get edges of my original graph. I'm going to pass in that so that we know how many edges we grabbed. Now I need to qsort. The way qsort works is I give it a pointer to the array that I want to sort. I give it the number of elements that I'm going to sort. I give it the size of each element. And then I give it a comparator function. So I need to write this comparator, right? So okay. Now I don't know, I think this is supposed to return a minus b. So we're gonna cast this to an edge pointer, right? Ooh. We'll do that, and then we'll return E1 weight minus E2 weight, right? This way, if they're the same, this returns 0. If E1 is bigger, it returns something positive. If E2 is bigger, it returns something negative. And I think that's what quicksort expects. So we're going to give it this compare edge function. What's wrong? Why are you mad at me? Int void void incompatible function pointer types, passing int void void to parameter of type int const void. Do you want these to be const? There we go. Okay, so we've sorted all of our edges. Now we can loop through the edges in order, in increasing order of weight, right? So this is easy enough. Now I can say for int I equals 0, I is less than num edges, I++. I'm going to look at edges at I. If an edge connects two connected vertices, skip it. So I can say if UF equivalent, right, in our components, and then I want to look at edges I dot source and edges I dot destination. If this is the case, then we skip. Otherwise, we insert the edge into our spanning tree, right? So what do? I say graph, add edge, graph. This will be edges I dot source, edges I dot destination, and then edges I dot weight. And then of course I want to mark the endpoints as now being connected. So I'm going to go ahead and say UF union, right? And I'll grab the source and the destination. Okay, so now we've ostensibly added this edge and unioned it together so that you now skip the appropriate rest of the edges. And then we can return, oh, I guess I want to UF destroy components here so that there's no memory leak. Okay. Now what do we do? Now we mark this is our fake main function. This is so cool. Okay. And instead of calling prims MST, let's include Kruskals, and let's call Kruskal's MST. And a semicolon. Okay. Does this compile? No, it doesn't. Ooh, fun. Why? Oh, okay. Did I forget to add this to my make file? Yeah, I did. I totally did. Okay, so Kruskals.o, and then just for fun, Kruskals.h. Okay, that compiles. Okay, so 65319. If I look at my graph.text, I keep the 65319. So again, I skip the 7 and the 8, and that sort of makes sense. I think that's the same, like, you know what? Let's be fun. I'm just gonna call this MST now, and I'm gonna have this take a parameter. So we'll say algo equals argv1. If c is less than 2, f print f standard error usage percent s prims for Kruskal's. And then we'll print argv0 here. And then, exit 1 or something. I don't know. Ooh, oh, you want me to include standard lib. Okay. Now we'll say char algo equals equals argv1 if string comp algo to prims, or if not string comp, right? Because this is sort of it returns a stupid thing. Let's say does this work? Right. Okay. So MST algo is now a type def for a function pointer that takes a graph and returns a graph. Right. So we can say uh, maybe I'm just going to compare this directly from argv1. Right. And so now I'll say MST algo. Now we can say algo equals, if it's prims, then it's going to be MST prims. Let me go back and include prims. Does this work? Oh, I called it prims MST. Okay. No? Do I have to throw that there? I don't know how function pointers work. Non-object type MST algo is not assignable. Do I have to maybe call it a pointer? Like algo. Oh, cool. Okay. So I guess that's how it works. Else if here, let's print let's do that. And then exit. And so now we know for a fact that this is the right thing. And so now we can just call algo. Okay. Does this work? Sweet. Okay. So now if I MST, okay, great. Okay. If I do prims, if I do Kruskal's, and it's the same MST both times. Okay, so what are the odds that we got both of them wrong, right? All right, I'm gonna call it here. Good night, everyone.